Welcome to the deep dive. You know how it works. You provide the brain food, and we dig into it for you.
Yeah, we sift through, find the good stuff, the key takeaways from the sources you send our way.
And today we're getting into some physics fundamentals, stuff that honestly you use and see every single day. You sent over this chapter on force, work, power, and energy. And we're going to focus particularly on, well, turning forces and uniform circular motion. Seems like you wanted to get a better handle on those.
Absolutely. So our mission really is to unpack the idea of moment of force, leverage, and then look at equilibrium. What does it mean for something to be balanced?
Whether it's sitting still or moving steady, right?
Exactly. And finally, tackle uniform circular motion. Sounds simple, maybe, but there's some neat stuff going on there. We're looking for those surprising bits and how it all connects to the real world.
Okay, let's jump in. Turning forces. The material you sent says basically when a force hits a solid object, it can do one of two things. First one's pretty straightforward, make it move in a line.
Right, like pushing a ball. That's called translational motion. Straight line movement.
But the second way is rotation. That happens when the force hits something that's like pivoted or hinged.
Yeah, think about pushing a door. It doesn't just slide, does it? It swings, rotates on its hinges. That's your rotational motion.
And that swinging, that turning, that's where this moment of force comes in. Or torque, they call it too.
Precisely. It's the measure of how good that force is at causing the rotation.
So it's not just about how hard you push.
No, not at all. It's just as much about where you push relative to that pivot point, that hinge. The calculation is the force multiplied by the perpendicular distance. So the distance measured at a right angle from the pivot to the line the force is acting along. Figure 1.3 in the chapter shows that pretty clearly.
Okay, so if I push with the same force, but further away from the hinge?
You get a much bigger turning effect,
Yeah.
more leverage.
Which we all kind of know, right? Try pushing a heavy door open right next to the hinges. It's really hard. Push out by the handle. Much easier.
Exactly. It's maximizing that perpendicular distance. And this turning effect, this moment, it has its own units. The standard is Newton meters, mm.
Force times distance makes sense. Newtons times meters.
And you might see older stuff using dyne centimeters.
Yeah.
The conversion's huge. Actually, 1 Newton meter is like 10 million dyne centimeters.
Wow.
Shows the scale difference. Oh, and it also mentions kilogram force meters and gram force centimeters. Those basically factor in gravity acting on a mass. But Newton meters is the main one for physics.
And it's not just how much turning, but which way, right? There's a sign convention.
Yeah, usually anti-clockwise rotation is taken as positive and clockwise as negative.
Right.
Just a way to keep track of the direction of the turn.
Okay.
And it's important to remember, moment of force isn't just a number, it's actually a vector.
Meaning it has direction.
Right. The direction is along the axis of rotation. So if you're turning something anti-clockwise, the vector points sort of outwards along that axis. Clockwise, it points inwards.
Like tightening a screw. Clockwise turns drive it in. The direction of the torque is in.
Perfect example.
The chapter gives some great everyday examples too. The door handle we mentioned, putting it far from the hinges, that's figure 1.5.
Yeah, and loads of other things, like those old hand flour grinders. Handles way out on the rim.
Ah, yeah.
For easy turn.
Or a steering wheel.
Yeah.
Push on the rim, tangentially. Push on the opposite side, it turns the other way. That's in figure 1.6.
Bicycle pedals too, right? Pushing down on the pedal gives you that distance from the axle. That's figure 1.7.
Definitely. And the classic one, a spanner or a wrench. Figure 1.8 shows this. Why do they have long handles?
More leverage, bigger turning distance.
Exactly. A small force on the end of a long handle gives you a big turning moment on the nut or bolt. Very practical.
Okay, then it introduces something called a couple. Not romantic.
Hey, no, it's physics. It's a pair of forces. They have to be equal in strength, opposite in direction, and parallel, but crucially, not acting along the same line.
So they don't cancel out completely. They cancel out in terms of straight line motion, yes, the net force is 0. But because they're offset, they always produce rotation. Pure rotation, actually.
Ah, okay. And it says even a single force on a pivot involves a reaction force forming a couple.
That's true, technically. But the clearer examples are things like, well, turning a water tap, you often use 2 fingers, pushing opposite ways. That's figure 1.10.
Or tightening a bottle cap, figure 1.11. You twist with your fingers.
Right. Turning a key in a lock, figure 1.12. The steering wheel again, figure 1.13, applying force with both hands often.
Yeah.
And yes, Bicycle pedals involve this too.
So how do you measure the turning effect of this couple?
That's the moment of a couple. You just take one of the forces, remember, they're equal, and multiply it by the perpendicular distance between the two forces. That distance is called the couple arm. Figure 1.42 shows it, and equation 1.3. Key thing. Net translational force is 0, only rotation.
Got it. Okay, so forces cause turning. What about when things don't turn or don't move? Equilibrium.
Equilibrium is when a body's state of motion, or rest, doesn't change because all the forces and moments acting on it are perfectly balanced.
No change. So it could be still or...
We're moving steadily. That gives us two types. First is static equilibrium. Static means still. Like a book on a table, it's not moving.
Or a balanced seesaw, maybe? Figure 1.15?
Perfect. All forces, all pushes and pulls, up, down, sideways, they all add up to 0. And the turning effects cancel too.
And the other type?
Dynamic equilibrium. Dynamic means moving, but moving constantly. So either in a straight line at a constant speed or rotating at a constant rate.
Like a raindrop falling at terminal velocity, it stops accelerating.
Exactly. Or an airplane cruising level at a constant speed. Or, interestingly, a stone being whirled in a circle at a uniform speed. It's moving, but in a steady, predictable way. The forces are balanced in a way that maintains that constant motion.
Okay, so what are the rules for something to be in equilibrium, static, or dynamic?
Two main conditions, according to the chapter. First, the resultant, the net effect of all forces acting on the body must be 0. They all have to cancel out. No leftover force to cause acceleration.
Makes sense. Prevents speeding up, slowing down, or changing direction in a line.
Second condition, the algebraic sum of all the moments, all the turning effects about any point must also be 0.
So all the clockwise turning has to exactly balance all the anti-clockwise turning?
Precisely. Sum of anti-clockwise moments equals sum of clockwise moments.
And that leads directly to the principle of moments.
Yep. For any pivoted body in equilibrium, that balance holds true. Sum of anti-clockwise moments, sum of clockwise moments.
Equation 1.4 states it?
And the classic example is a beam balance, like the old scales.
Exactly. It works entirely on that principle. The chapter even details an experiment to check this out. You take a meter rule, pivot it, hang weights off it.
Like in figure 1.16.
You adjust the weights, $20 and $20, and their distances from the pivot, $1.22, and you find it balances perfectly when nully dollar times lowers 2 times nullers times 2. Weight times distance on one side equals weight times distance on the other. Verifies the principle.
It does. And then there are those numerical examples, 1 to 10. They're really useful for seeing how to actually use these ideas.
Yeah, calculating torque on a wrench, force needed for a door, balancing things. It helps make it concrete.
Definitely. So that covers turning and balancing. Ready to move on to circular motion.
Let's do it. Uniform circular motion. The chapter defines this as moving in a circle at a constant speed.
Right. Constant speed is the key part of uniform. But, and this is crucial, the velocity is not constant.
Because velocity includes direction.
Exactly. And if you're moving in a circle, your direction is changing all the time, even if your speedo reads steady. Figure 1.42 shows the velocity vector pointing off tangents at different points on the circle, always changing.
And if velocity is changing,
then there must be acceleration. Even though the speed isn't changing, it's a change in direction that causes acceleration here.
So uniform circular motion is accelerated motion. Unlike uniform linear motion, which is straight line, constant speed, 0 acceleration.
You got it. That's a really important distinction.
So if it's accelerating, there must be a net force causing that acceleration, right? Newton's laws.
Absolutely. And for circular motion, that force has a special name. Centripetal force. Pedal-like seeking, centri for center. It's a center-seeking force.
Ah, okay. So it's always pulling the object towards the center of the circle, like in figure 1.43.
Always. It's the force that's constantly redirecting the object, stopping it from flying off in a straight line, which is what inertia would make it do otherwise.
It's like the string pulling on a ball you're swinging around your head.
Perfect example. The tension in the string is the centripetal force in that case. The chapter gives others too, the electrical force holding an electron near a nucleus.
Or gravity holding planets around the sun or the moon around Earth.
All those are examples of forces acting as the centripetal force required to maintain circular motion. And it notes that bodies in uniform circular motion are technically in dynamic equilibrium under this force.
Okay, but then there's this other term, centrifugal force, which sounds like the opposite fugal as in fleeing. Center fleeing.
That's right. It's described as a force acting away from the center. It's that sensation you feel, like being pushed outwards when you're in a car turning a corner sharply.
So is it the reaction force to centripetal force?
Ah, good question. But no, the chapter is clear on this. It's not the Newtonian reaction paired to the centripetal force. It's actually, well, it's called the fictitious force.
Fictitious, meaning it's not real.
It's not a real force in the sense of resulting from a physical interaction like gravity or tension. It's something that appears to exist when you are observing from within the rotating system, the rotating frame of reference.
Okay, that sounds a bit weird. How does that work?
The merry-go-round example in figures 1.44 and 1.45 helps a lot. Imagine someone standing outside, watching a ball being swung on a string attached to the merry-go-round. They see the string tension pulling the ball inwards, the centripetal force making it go in a circle. Simple enough.
Right.
But now imagine you're sitting on the merry-go-round, rotating with it. From your perspective, the ball might look like it's just hovering there, stationary relative to you.
Okay.
But you know the string is pulling it inwards, centripetal force. To explain why it's not accelerating towards the center in your rotating view, you invent an outward force that perfectly balances the inward tension. That invented outward force is the centrifugal force.
Ah, I see. So it's like an accounting trick for someone inside the rotating system to make Newton's laws seem to work from their non-inertial perspective.
That's a great way to put it. The real force is the centripetal one, the tension. If the string breaks, the outside observer sees the ball fly off straight, tangent to the circle. The person on the merry-go-round sees it fly radially outwards as if pushed by that centrifugal force.
So centrifugal force is a consequence of being in that accelerating, rotating frame.
Exactly. The chapter calls it a fictitious or virtual force, a concept needed to describe motion in these non-inertial frames, but not a fundamental interaction itself.
Wow, okay, that clarifies the difference. So wrapping this deep dive up.
We looked at how forces create turning effects moments, or torque, depending on force and distance.
We saw how equilibrium requires a balance of both forces and moments, leading to the principle of moments.
Sum of clockwise equals sum of anti-clockwise.
And then we dived into uniform circular motion, seeing it needs a real inward-pointing centripetal force to keep changing the object's direction.
While the outward centrifugal force is more of a perceived effect, a fictitious force experienced within the rotating frame itself.
So, a final thought for you, the listener, to chew on. Think about other times you see curves or rotation or things just staying put. A car turning, a satellite orbiting, maybe even stirring your coffee.
Yeah, how do these ideas moment equilibrium centripetal force apply? What are the real forces doing the work? Sometimes the physics is hiding in plain sight. In really simple-seeming situations, it's kind of fun to try and spot it.